Hello students, today we are going to start our second lecture on current electricity. In previous lecture we have seen Ohm's law, then we have discussed about the relation between resistance and resistivity. There we have seen that resistance is depending on the dimension of the conductor, basically directly proportional to the length and inversely proportional to cross sectional area. Then we talked about how resistivity is independent about the dimension of the conductor, and we also discussed about the resistivity is depending on the temperature, that is if temperature increases the resistivity also increases, and if temperature decreases the resistivity also decreases. This thing we have seen, and we have seen also J equal to sigma E, that is J equal to your current density and sigma is your conductivity and E is your electric field. This thing we have seen. Now in today's lecture we are going to prove all these things. Let's say the resistance is depending on the dimension of the conductor, so this thing we are going to prove here. And we have talked about the resistivity is depending on the temperature, so that thing also we are going to prove here. So let's start today's lecture. So we'll see motion of free electron in a conductor. So let's take a conductor here. This is a conductor here, and we'll talk about motion of free electron in a conductor without any electric field. So whenever you take a conductor, this is the area of the conductor and this length is L, right? And inside this conductor there is many free electrons are there. Many free electrons are there. So these free electrons inside the conductor is moving randomly. So first thing here it is that free electrons are moving randomly. Randomly means they are moving in every direction. These electrons are moving in every direction, and you will ask from where they are getting their speed. If they are moving from there, where they are getting the speed? You see here, I can relate one thing here, that is half mv square equal to 3 by 2 kBT. That is from the kinetic theory of gases, if you remember. So if I put room temperature 300 Kelvin here and mass of the electron here, I will get, let's say put U here, I will get U in the order of 10 to the power 5 meter per second. At room temperature, you take a conductor and you put here, and in that conductor the electrons are moving with this much speed, and this speed is basically called as thermal speed of electron. So due to the temperature, these electrons are moving with 10 to the power 5 meter per second inside the conductor, right? If these electrons are moving in random direction, they are moving in all direction, then you can say that the average velocity of electrons is 0. Why it is 0? You can imagine, let's take a electron, this is electron number 1 which is moving with u1 velocity, electron number 2 this is moving with u2 velocity, electron number 3 this is moving with u3, electron number 4 this is moving u4. Like that there is n number of electrons, large number of electrons are there, and all are moving randomly in every direction. Clear? So that means I can say that average velocity is equal to u1 plus u2 plus u3 plus un divided by n and that is equal to 0. So all these electrons, if you take, the average velocity of electron will be 0, and these are moving with 10 to the power, one electron is moving with 10 to the power 5 meter per second speed, right? It's a very huge speed here. Okay, now let's talk about the motion of one electron. If I take one electron here, this electron will move and get collide with the lattice side or positive ion. This will collide with the positive ion, or you can say the lattice side, and change its direction and come here again, get collide with the lattice side, and it will move like this. Clear? In this process, the electron is not going to change its speed, only the direction of electron is going to change, but the speed is not going to change. The speed after the collision, whatever speed it has, after the collision also it will have the same speed. The electron will have the same speed, but the direction is changing here after the collision with the lattice point or the positive ion. Clear? Next thing, we defined a average relaxation time. Average relaxation time. So this is denoted by tau. What is average relaxation time? First listen about relaxation time. So relaxation time is defined as, let's say the electron from here start from here and collide here, right? This is one collision, first collision, this is second collision, you can say. So relaxation time is defined as the time taken by the electron in between two successive collision, right? So between two successive collision, how much time the electron is taking, that is called your relaxation time. Let's say it is taking tau 1, first electron is taking tau 1 time. Clear? And second electron is taking tau 2 time, like that. So you can say that tau equal to, that is average relaxation time equal to relaxation time tau 1 plus tau 2 plus tau 3 tau n divided by n. This is called your average relaxation time. Clear? And here one thing I will tell, these electrons are moving with this much speed, it's a very huge speed, and due to motion, these electrons are moving in random direction, the motion is random. So I can say that if I choose an area, cross-sectional area like this, let's say I choose a cross-sectional area like this is a cross-sectional area, you will say if the motion is random in this direction, let's say 10 number of electron is moving in delta t time, you will say that means along this direction also 10 number of electron are moving in delta t time, because this motion is random. So along this direction the current will be I, and along this direction the current will be I. Clear? So the net current will be 0, right? The net current will be 0. So in presence of the temperature or without electric field, what you will get, the current in the conductor will be 0. Or you can take this like cross-sectional area, the current along this direction I and along this direction also I, so I will get I net will be 0. The current is 0 here. Clear? This thing will happen without electric field. Clear? Now we will go to see what happens if electric field will present, right? So here I am drawing. Again this is your conductor, and this is your cross-sectional area. I can write this is cross-sectional area A, and this length is your L, right? Now you apply electric field in this direction. You apply electric field in this direction. So due to this application of electric field, you know from the electrostatic what will happen basically, the negative charge will come and get accumulated here and the positive charge will be this side induced on the surface of the conductor, right? You can take this surface of the conductor, not inside the conductor, here you can put the surface of the conductor, so it will on the surface of the conductor it will induce. This is going to be the electrostatic condition, but I need a current in the circuit, right? So what I will do, I put an electric field and I join a conductor like this, a conducting wire like this. So due to joining this wire, the electron will flow from this side and move like this, and there will be a current flow. There will be a current flow in the conductor, right? So the electron will be flow from here and the current will be opposite to the motion of the electron, right? So instead of putting any external electric field and joining a conductor like this, what I do now, I am just removing this. What I will do now, what I will do, I put a battery and connect these terminals here. So battery you may not know. Battery one will see in the next class what battery actually does. Battery actually, the work of battery is to maintain constant potential difference between two terminals. So it is working like a external electric field, you can say, right? And this conductor if you join here, then there will be a flow of electrons. So now what will happen, there will be no induced current now, induced charges here, there will be no induced charges, this side also no induced charges, because charge are now flowing. In the very first lecture we talk about, right, electric field inside the conductor is not zero, because there will be no accumulation of the charges. Here there is no accumulation of the charges. Clear? So V potential is like this. This is higher potential, this is lower potential. You can say that the electric field is direction will be along this direction. Now whatever electron in the free electron in the conductor, there will be force on the electron along this direction, right? And this will be moving like this in the circuit. If the electron are moving along this direction, you know that the current direction will be opposite. This will be your current direction. So electron motion, direction of motion of electron is opposite to the direction of motion of the current. This thing is going to happen. Let's see in the picture of one electron here. So this electron is moving like this. Previously we have seen. Then there is a positive lattice is sitting. Then it will get collide, and the same speed it is coming, and again collide, again move. This will collide like this, and it will be like this, collide. Right? This is going to happen in the conductor if there is no electric field. This is going to happen. Now you apply a electric field here. Now there is a electric field you apply. So if you apply a electric field, now the electron get accelerated, right? Or the electron will move opposite direction of the electric field. So now what is happened, by dotted line I am showing that electron will be slightly drifted and reach here and collide whatever positive lattice is sitting here. Similarly, it will change its direction after that and come here and reach here. Then it will move like this and it will come here and reach here. Right? It will collide here. Basically, these are positive ions or lattice point. This is going to happen. So here I am, that solid line is for without electric field, the dotted line is your with electric field. This is going to happen. Now see, this is a picture of only one electron. This electron is get drifted opposite direction of the electric field. The electron is moving along this direction, slightly drifted. Now you take all the free electrons inside the conductor. All the free electrons, now what will happen? Like this electron, it is get drifted opposite of the electric field. All the free electrons inside the conductor, they also drifted opposite of the electric field. Whatever motion they are doing previously, but as soon as you apply electric field, what will happen? These all electrons will be drifted opposite of the electric field. That means there will be a net motion of the electrons opposite of the electric field. Not only one electron, all the electrons will be drifted along this direction. Clear? Due to this motion of these electrons or drifting of that electron, there will be a net current in the circuit. Okay, there will be a net current in the circuit. We'll see now. So let's say I want to write down for this electron the speed or velocity. So V1 is the velocity of the electron at any time. So I can write this is U1. U1 is due to the thermal. Without electric field we have seen this U1, right? This random velocity they are moving. This is U1 plus acceleration into T1. Got it or not? Now because of this electric field there will be a acceleration, right? And you know that what should be the acceleration here? Acceleration will be minus E divided by m. This will be your acceleration. This is the mass of the electron. Clear? Now this is force basically divided by mass, right? This is acceleration. So if I want to write V1, I can write U1 plus minus E divided by m into T1. V2 can be written as U2 plus minus E divided by m and T2. Similarly, I can write Vn for nth electron. This is Un plus minus E divided by m into Tn. This is going to happen. Clear? So now I want to find the average velocity of electrons. So average velocity of the electrons if I want to find out. So you will say that average velocity will be V average is equal to simply V1 plus V2 plus Vn divided by n, because n number of electrons we are taking. So V average will be, we can write V1 can be written as U1 plus this thing I am separating. I just write U1 plus U2 plus U3 plus Un divided by n plus, here you will see this is minus E divided by m. This will be your T1 plus T2 plus T3 Tn divided by n, right? This will be your average velocity. If you see here, this velocity is going to be 0, right? This is going to be 0. This thing we have seen in without electric field. Here if you see, the average velocity is 0 because all are moving in random direction. And this term you know that average time will be your relaxation time. So here I can write V average is called your minus E divided by m into tau. This is your average relaxation time. This V average also called your drift velocity. This is also called drift velocity, right? So what is a drift velocity now? Drift velocity basically defined as the average velocity of electrons in presence of electric field. So here I am writing. So this is called also drift velocity. Why it is called drift velocity? Because the electron is get drifted due to the presence of the electric field, and drift velocity is defined as average velocity of electrons. This can be written as average velocity of electrons. So here I am doing. So average velocity of electrons in presence of, or you can say that in presence of electric field. This is the average velocity of electrons in presence of electric field. This is called your drift velocity or average velocity of the electron, right? So what relation we got here? We got Vd or V average is equal to EE minus of EE divided by M into tau. If I write down in modulus or the scalar form, this will be magnitude only I am writing. This will be EEM by into tau. This will be your drift velocity, right? This thing we got to know. That means the electrons are moving in a conductor with the velocity that is called drift velocity, right? One thing, and the drift velocity will come in the order of 10 to the power minus 4 meter per second. See here, this drift velocity is very small velocity. There the thermal velocity is coming 10 to the power 5 meter per second, but it is not giving any current. But here the drift velocity is coming as 10 to the power 5 meter, 10 to the power minus 4 meter per second, and also it is giving a current. Because now what you got here? You got here that slightly movement of electron, slight movement of electron can give a current in the conductor, right? And that to be in one direction they have to all the, because here in the application of electric field all electrons are moving in the same direction, right? All electrons are moving in the same direction. Clear? Then we getting the drift velocity. Okay. Now let's talk about the electrons in the conductor. Let's say this is a conductor, and we are now proving the relation between the current and the drift velocity. Okay, so this is a conductor and this area is your A and this length is your L, and the, let's say charge Q, let's say the charge Q inside the conductor, and it is moving along this direction. Similarly, lots of charge is flowing along this direction. If you take a positive charge, and you will say that the current direction will be along this direction, right? And obviously this side is V1, this side is V2. So V1 is greater than V2. V1 potential is greater than V2, right? The positive charge is flowing along this direction. So I know that current can be defined as current equal to total charge flowing through this conductor divided by the time taken by the charge to flow through this conductor, right? This is the current flowing through this conductor. Let's say t equal to, this is the time t, and this is t equal to t plus dt. This is the condition, right? Now here you can say that how much time it is taking, you will say that dt time it is taking, right? So I can put here dt here. So this will be dt time it is taking. Clear? It is t time it is going and t plus dt. Okay, and you know that all the charges is moving inside the conductor with the drift velocity. They are moving with drift velocity, right? That is Vd. Here I am taking the positive charge, nothing different here. I am only taking the positive charge, right? And we will put the negative charge, q equal to negative we will put, and we will get the drift velocity for the electron also, or current due to the electron also, right? So total charge divided by dt. So total charge flowing through this conductor can be written as n into q. N is the number of charges here, divided by dt. Clear? Now see here. So I can write that n is the total number of charge here, right? So I define small n is number density of the charges, that is capital N divided by volume of the conductor, that is n divided by volume of the conductor is A into L, length of the conductor. This I can write, right? Volume will be area into length of the conductor, because this is cylindrical conductor we have seen, and that will come. Now current can be written as I equal to n, in place of capital N I just write small n into A into L. This will be small n, that is number density, A into L, right? And there will be q charge is there divided by dt. Clear? And you see here, if the charge is starting from this point, this side, and reaching this side, how much time it will take? You will tell that this is dt time it is taking, and how much speed it is moving? With Vd speed it is moving, with drift velocity. So here I can say another relation, that is Vd into dt will give you the length of the conductor, right? So here I can say that this can be written as NAQ. In place of length I can write Vd into dt, that is Vd into dt divided by dt. So dt get cancel out, so this will get NAQVd. This is your current, right? This is a very important relation you have to remember. If you put electron, right, if you put electron, this will be I equal to minus NaEVd will come, because the charge is negative now, right? And electron obviously move opposite of the, because if the positive charge moving along this direction, the electron will move along this direction, opposite to the electric field basically, right? Or electron will move from lower potential to higher potential, right? This will be going to the current and this relation. If I write down the magnitude here, this I equal to NAEVd, this is drift velocity, right? So, and I can write J equal to, that is I by A is equal to NEVd, right? This is very important formula, you have to remember all this thing. So here N equal to what? Number density of electrons, right? Number density of electrons or number density of charges you can say, right? Or here I am writing general way, number density of charges. What is E? E is the charge, right? And A is the cross-sectional area of conductor, right? Vd you know, that is drift velocity. Here I can write Vd equal to your drift velocity. Clear? This relation is very important, you have to remember, right? Now what we got here? We got three equations. First one, if you remember, we got J equal to sigma E, right? In the scalar form, if I write, that is J equal to sigma E, right? Second thing I got, that is Vd, drift velocity, equal to E divided by m into tau, right? This thing I got, drift velocity. Third thing I got what? I equal to NAEVD. These three things I got, right? Three formulas I got, and this three formula is very important. You have to remember these three formula, right? Okay. Now here I got J equal to sigma into E, and let's say this is your equation number 1. I got Vd equal to E divided by m into tau, that is equation number 2, and I got I equal to NAVDE, that is equation number 3, right? This thing I got, right? So you just from 1 and 2, what I can write? J equal to sigma into E, right? From 1 and 2, from this one equation equal to J into sigma into E, right? Then here I can say that in place of E I can put all this relation, right? I can put, so I can put here J equal to sigma into A, and here I can write sigma into E can be written as Vd into m divided by E into tau. This relation I can write. So sigma into this much, right? So electric field value is Vdm divided by E into tau. Clear? This is one relation we can derive. Now, if you see these two relation, that is 2 and 3, if you see, so you can say that I equal to NAE, in place of Vd you write EE divided by m into tau, right? So I can write here what? So I can say that this is coming NAE square, right? NAE square, and this will be your divided by m into tau into electric field. This will come. So here it will be NE square tau divided by m, right? And this will be your area, and electric field can be written as delta V by L. Delta V by L. L is the length of the conductor, here you can see. So electric field can be written as delta V by L, V1 minus V2 by L, right? This relation you have seen in the, this is potential difference basically, right? Delta V by L. So this is your I. So I equal to what I got? NE square tau divided by m into A by L into delta V. Clear? This I got. And from Ohm's law I know that, from Ohm's law I know that delta V equal to I into R. So you can find out R value here, from here. So R equal to, you can see here, it is coming as m by NE square tau multiplied by L by A, right? This thing you got. resistance value will be now this much. You know that rho equal to RA by L, or you can say that R equal to rho L by A. So if you compare this equation, let's say this is your equation number 4 and this is your equation number 5. So if you compare these two equations, what you will get? So rho equal to M divided by N E square tau. This will be your resistivity. First thing you observe here, that resistance is depending on length of the conductor and area of cross section of the conductor, right? So resistance is depending upon the length and area here. This thing proved here. Now if you look at this resistivity, this is depending on the number density of the electron. So resistivity is inversely proportional to the number density of the charges in a conductor or number density of the electron or charge carrier, and this also proportional to 1 by tau. Tau is what? Relaxation time of the conductor, right? Tau is the relaxation time of the, or average relaxation time of the electron in the conductor, right? 1 minute. Right? So average relaxation time of the conductor. Okay. So now this thing, you know that it depends on the temperature. How? Because if I increase the temperature, then what will happen to the relaxation time? If I increase the temperature, the electron speed will be increases. So it will be going faster than previously and collide with the lattice point. So the time taken between two successive collision is going to decrease now, right? So if the time taken by the successive collision is decreased, so I can say that with increase in temperature, if temperature will increase, that leads to decrease in the relaxation time. Relaxation time will be decreasing, and that leads to, if relaxation time is decreasing, you will obviously say that resistivity increases, right? Again I am repeating, if you increase the temperature, the speed of the electron in the conductor will increase. Due to increase in the speed, the electron will move faster and it will collide to the lattice point very fastly. That means, let's say previously it was taking very less 10 to the power, just example I am giving, let's say it is taking 1 second, now it will take half second. So now because of increase in temperature, this relaxation time is going to decrease, right? And you know, this time is obviously in the order of 10 to the power, you can say minus 14 or something, minus 14 seconds, very less time it is take, right? So this relaxation time is going to decrease, clear? So due to decrease in relaxation time, there will be increase in the resistivity. This resistivity will increase. Similarly, if you decrease the temperature, the relaxation time will be increase and the resistivity will decrease. This is going to happen in the conductor. This is true for what? This is true for only for conductor. For semiconductor, I told that this will not hold, this will be different. So here you can see that if the resistivity is depending on temperature, then resistance also depending on the temperature. Though resistance is depending on the dimension of the conductor, but it also depending on your resistivity, right? Resistivity is changing with temperature, that means resistance also changing with temperature. Same thing will hold for the resistance. Temperature increases, tau decreases, that leads to resistance increases. Temperature decreases, resistance tau increases and resistance decreases, right? This will going to happen. So with temperature this thing will, again this is true for only for conductors, right? This is going to happen. Clear? Okay, now we will prove all this thing. Now we have seen whatever we talked there. Resistance is depending on length and cross sectional area, that thing we have seen. Resistivity is depending on the temperature, that we also seen. And look at this thing, resistivity is inversely proportional to number of charge carrier in the conductor, right? Or number of free electrons you can say here. So in this case, if the number of free charges will be more, the resistivity will be less. More number of free charges, the resistivity will be less. Less number of free charges, the resistivity will be more, right? So depending on that, you can decide that gold and your iron and all these things, the resistivity is depending, right? Because there will be a number density different in the different type of material, right? Okay. This thing is done. Now let's do some problem here, right? Let's do some problem. Now we'll got to know all this thing. Now we'll do some problem here. The velocity of charge carrier of current about 1 ampere in a metal under normal condition of order. So there is a current 1 ampere and you know that velocity is, they are talking about drift velocity, and you know that drift velocity is coming 10 to the power minus 4 meter per second, in the order of 10 to the power minus 4. So you see here a fraction of mm per second. Yes, this is the fraction of mm. So this option will be correct. So velocity of that light, it is not true. Velocity of light it is not, because the motion of the electron or the velocity of the electron is your drift velocity, and that is called 10 to the power minus 4 meter per second. So several thousands meter, not, that is not also true. Few hundreds meter per second, this is also no. So few hundreds meter, you can say that this is for the thermal, because in thermal velocity of the electron is coming around 10 to the power 5 meter per second. Clear? Now go for the second thing, second question. Across a metallic conductor of non-uniform cross section, a constant potential difference is applied. What it is saying that now they are talking about non-uniform cross section. Let's say this is the non-uniform cross section. This can be a non-uniform cross section because here area will be small, here area will be bigger, right? The quantity which remain constant along the conductor, right? Constant along the conductor. Okay. Metallic conductor, uniform constant potential. Constant potential means I will join a battery. That thing I told, right? Battery work is to maintain constant potential difference between two ends of a conductor, right? We will see in the battery all these things, but you remember now to maintain constant potential difference at two ends of the conductor, right? So you see here now. First of all, in the conductor there will be no accumulation of charges. So no accumulation of charges. Like in electrostatic there will be accumulation of charges. First lecture we have talked about this thing, right? Because this charge is keep flowing in the circuit. So if there is no accumulation of charges, that means the current is always same. The current will be same, right? The current is not going to change because there will be no accumulation of charges. So you can say that the current will be same here. Let's talk about all this option. So let's talk about drift velocity. Let's first talk about the current density. Let's say. So if the current is same everywhere in the circuit, if I ask about current density, J equal to I by area, perpendicular area. Here the area, cross-sectional area is increasing from left side to right, it is keep increasing. If it is increasing, then you will say that J is not a constant. It is not a constant. right? Because this area is keep increasing, right? Here you can say that if the current is flowing here, the area is increasing, so J is decreasing because the area is increasing here. Area is increasing, the J is current density is decreasing, because here let's say area A1, here A2, you know that A2 is greater than A1. Now let's talk about electric field. So you know that J equal to sigma E. If the current density is decreasing, then electric field also decreasing, right? So electric field also again not constant here. Here electric field is not constant, electric field is keep changing. Clear? Now come from the drift velocity. So J is decreasing, so electric field also decreasing. Now drift velocity, you know that Vd equal to E divided by m into tau. If electric field is decreasing, then Vd also decreasing. Clear? This is going to happen here if the current is flowing here. Then only current will be constant quantity here, because there is no accumulation of the charges. Clear? Whatever charge is flowing, that is flowing. There will be no accumulation of charges. If there will be accumulation of charges, then the flow of charges will be reduced, right? Then there will be current will be less. But there is no accumulation of charges. Now go for this question. In the given figure, a battery of EMF E is connected across a conductor PQ of length L and different area of cross section having radius R1 and R2, right? And R1 is greater. This is basically R2. They have given this is basically R2. Oh, sorry. This is basically your R2 and this is basically your R1, right? So you see here, this is opposite of the same thing, right? What we did now. What will happen here? Choose the correct options as one move from P to Q. So the current is flowing from P to Q. Clear? Drift velocity of electron increases, electric field decreases, electric current decreases, all of this. First of all, there will be a constant current will be flowing. So I is what? Constant. That thing we have seen, because there is no accumulation of charges here. I is constant. Constant current is flowing here. Clear? Now this conductor is like this. This is your radius R1 and this is your radius R2, and R1 is greater than R2. So this area will be bigger and this area will be smaller, right? And the current flowing along this direction. Now you see, if I calculate the current density, that is I by A, if the current is flowing along this direction, gradually the area is keeping decreasing. The cross-sectional area will keep decreasing. If area is decreasing, then you can say that J is increasing. Clear? The J is increasing. Current density is increasing. If current density is increasing, and there is a relation, I can write J equal to sigma E. If current density is increasing, this electric field also increasing here, right, along this direction. And I know that Vd is equal to E divided by m into tau. So if E is increasing and this Vd also keep increasing, right? Now you got all the thing, you just see. Drift velocity of the electron is increasing. Yes, the drift velocity of the electron is increasing. This is true. Electric field decreases. No, electric field is increasing here. This will be false. Electric current decreases. Electric current is constant here. Electric current is constant here. So this is also. All of this is not. So option number 1 will be your correct option. Clear? Done, right? Now we will define another term that is called mobility, and it's very important physical quantity, because in semiconductor also it has importance. In conductors as well as semiconductor, it has importance. So mobility basically defined as the drift velocity per unit electric field. This is the magnitude of drift velocity per unit electric field, and it's a scalar quantity. This is a scalar quantity. And unit you can write, this is velocity per unit electric field. If you write, this will come meter square per volt into second. You can say here this will be, if I write the unit here, so if I write the unit here, so Vd is the drift velocity, right? So this will be meter per second. And electric field can be written as here V by L, right? Or volt per meter, right? Volt per meter you can write electric field. So this will be meter square divided by volt into second. That thing is written here, right? So unit will be meter square per unit volt into second. And dimensional formula, so this will be volt into second, right? So dimensional formula you can find out. This is m minus 1 L0 T2 I to the power 1. That is your, this is your I you can write, or A1 you can write. Anything you can write, right? So you can find out the dimensional formula. You know the dimension of the drift velocity, you know the dimension of electric field as well, right? So you can find out. Previously also we have seen how to find out the dimension of electric field. You just try it and you will find out this relation. Now Vd, you know that Vd is what? E tau divided by m. So mobility can be written as E tau divided by m, because you put this formula here, electric field get cancel out, this will be E tau by m. And tau is the average collision time for the electrons, or average relaxation time, right? So here if you see this relation, mobility is depending on the mass of the charge carrier. So if you take positive charge, then there will be mobility will be different. If you take negative charge, then the mobility will be different. This importance will come in the semiconductor part, but you remember now this mobility is going to depend on the mass of the charge carrier, because there will be in semiconductor we will going to see sometimes electron will be helping in flow of current, and sometimes holes, right, will be helping in flow of the current, right? So you remember this thing. Now mobility also depends on the temperature. How it is depending on temperature? Because we have talked how this tau, average relaxation time, is depending on the temperature. If temperature increases, tau decreases, right? So if temperature increases, this tau decreases, and if tau decreases, the mu decreases. That is your mobility decreases. With increase in temperature, the mobility will decrease for the conductors. This is for the conductor, right? For conductors, if you increase the temperature, the mobility will decrease, right? This is going to happen. Clear? This is mobility, and you remember this is a scalar quantity. And how you define this one? Drift velocity, or magnitude of drift velocity per unit electric field. This you define like this, correct? Let's do one problem. So what it is saying, a charged particle having drift velocity they have given, Vd they have given 7.5 into 10 to the power minus 4 meter per second. And electric field they also given, E equal to they have given 3 into 10 to the power minus 10. Clear? Volt per meter. Has mobility, they are asking to find out mobility in this m square v minus 1 s1, that is SI unit, right? So you can say that mobility basically defined as Vd, that is 7.5 into 10 to the power minus 4 divided by 3 into 10 to the power minus 10. So this will be 7.5 divided by 3 into, we will say here it will be 10 to the power 6. So it will be, how much it will come? So it will be 2.5, right? So you can see that this will be 2.5 simple, 2.5 into 10 to the power 6. So which option will be your correct? So this will be option number 3 will be correct. 2.5 into 10 to the power 5 meter. And this unit you see here, they have given, you can write here, right? This is the mobility. You apply that formula and easily you will get, right? Now we will see the temperature dependence of resistance. We will talk about, right? Now we will talk Recently we have talked about that resistance how depending on the temperature. Now we'll see this thing, right? So what is basically happen that, let's say R naught is the resistance at temperature T naught and R is the resistance at temperature T, right? And R minus R naught is called your delta T, delta R, right? Change in resistance. And here what assumption I am taking, this T is greater than your T naught, right? This temperature is greater than T naught. If the temperature increases for the conductor, you know that resistance also increases. Clear? So R minus R naught is delta R. Experimentally it is found that delta R is proportional to the R naught, initial resistance, right? At T naught whatever the resistance is there, that is proportional to R naught. And experimentally also it is seen that delta R is proportional to your delta T. Delta T is what? So delta T will be T minus T naught is called your delta T, right? So experimentally this thing will be observed, right? So you can say here that delta R is proportional to R naught into delta T, right? R naught into delta T. So delta R is equal to, you have to put a proportionality constant. This proportionality constant is your, I am putting alpha. This is your alpha and R naught delta T. We'll talk about this alpha. What is this? Let's derive this one, then we'll talk. R equal to is for delta R equal to what? R minus R naught equal to alpha R naught delta T. So R can be written as R naught 1 plus alpha delta T. Clear? This will be your relation. Resistance at temperature T can be written as R naught into 1 plus alpha delta T. Clear? What is alpha? Alpha is basically coefficient, or you can say that this is the thermal coefficient. This is the thermal coefficient of resistance, right? Thermal coefficient of the resistance. And if you write down its unit, it will be temperature inverse, right? It's temperature inverse. Clear? This is the unit of the alpha. Now from this relation you can say that the same thing will happen to the resistivity also. So I can write rho equal to the resistivity at any temperature T is equal to rho naught. This is the resistivity at temperature T naught to 1 plus alpha delta T. So here this alpha is different meaning. Here this alpha is called thermal or temperature coefficient or thermal coefficient, you can say that. So I am writing this thermal coefficient, or you can write this one is temperature coefficient also, you can write. Better to write temperature coefficient, right? Here you can write this is temperature coefficient of resistivity. This is the temperature coefficient of the resistivity. Clear? This thing you have to remember. So rho is the resistivity at temperature T, rho naught is the resistivity at temperature T naught. Clear? Okay, this relation you got, right? So this is very important. So you have to remember these two relation. This is one and this one. These two relation you have to remember, and from this there are many times they ask question from this relation, right? And here also the coefficient of resistivity unit will be your temperature inverse, right? Temperature inverse, right? Now let's see here what is basically happening. First look at this picture, right? Because this equation is suggesting you that resistivity is directly proportional to the delta T or temperature, right? Because it's directly suggesting you. So you just first look at here. So you see it is resistivity, this side it is resistivity. I just took it from the NCERT. This you can see from the NCERT also. So this side it is resistivity and this is temperature. And this is the resistivity of nichrome as a function of temperature. You see here the resistivity is like a straight line, and at 0 temperature there will be some resistivity existing here. It's not like at 0 its resistivity is 0. Just remember that at 0 also there will be some finite resistivity will be there, because the random motion of the electron, there will be some resistivity will be there, right? So now you see here it is a straight line and it's following this relation, right? Rho equal to rho naught 1 plus alpha delta T. So it's following this one because this is directly proportional, right? Resistivity, if you write down this one, this will be rho naught plus rho naught alpha delta T. So it is depending on directly depending on the temperature, so it will be a straight line. But if you look at here it is not a straight line. So this curve is varying like exponential, right? From here this, then it's not satisfying this equation, right? So actually this is we impose some limitation and derive this formula. If I derive the general formula, it will look like I will derive now, but you should not follow this derivation. You just, for NEET this is enough. You can do any problem asked in NEET with this formula or in your board exam. But for JEE Advanced, if you see this, for that I am deriving this one, but for NEET people it's not required. So what basically happening that, let's say at temperature T the resistance is R. At temperature T plus dt, at temperature, this general derivation I am doing, temperature T plus dt, this is R plus dr, right? And I know that dr is proportional to R and dr also proportional to the dt. These two are experimental. Experimentally these two are seen, right? So here I can say that dr is proportional to R into dt, right? So I can write dr is equal to alpha R dt. Alpha is your temperature coefficient here, right, of resistance. So here I can write dr by R is equal to alpha dt. Now I integrate here, resistance will be moving from, let's say, R0 to R, right? Let's take at T0 temperature there will be the resistance will be how much? R0. That thing any limit I am taking, resistance is R0 I am taking. At T temperature the resistance is R. So this will be T0 to T. So this is coming ln R and the limit will be from R0 to R is equal to alpha dt, that will be T minus T0 simply. That is your alpha delta T. Okay, so here I am writing. So this will be, if I write here, this will be, or I can write here also. So from here I can write, so ln R by R0, ln R by R0 is basically equal to alpha delta T, clear? Or you can write R equal to R0 e to the power alpha delta T. This relation you got, R equal to R naught into alpha delta T. Clear? So what relation you got? R equal to R naught into alpha delta T. This relation you got. If alpha delta T is very small, so if alpha delta T is less than 1, it's a very small number, you can write R equal to R naught 1 plus alpha delta T. For this type of material, this is basically a nichrome. For nichrome, the alpha delta T is very small. That's why it is satisfying this one, right? Similarly, there exists other material also, nichrome and your chromium. So this is basically, nichrome is made up of a alloy, which is nickel, iron and chromium, right? And similarly, there will be manganese and constantan. These materials have very small alpha delta T, right? So that's why they are varying linearly with temperature. But really what is happening that this is not straight line. This is going to be like this. R equal to R naught alpha delta T. If R equal to R naught alpha delta T, you can say that rho equal to rho naught alpha delta T, right? It's exponentially increasing, and temperature T, there will be a finite resistance will be there. Here you see, it's not starting from 0. Keep in your mind, it's not starting from 0. At 0 Kelvin, there is some temperature here. So there is some resistivity is there, and it's like this. So this is the resistivity of copper as a function of temperature, and you see this relation here. This is for if alpha delta T is less than 1, this will hold, and this is the formula we have seen, correct? So whenever this alpha delta T is very small, it will follow like this. Whenever alpha delta T is not very small, this will follow like this, correct? And for all conductors, this alpha delta T is not smaller than 1 or very small quantity. Clear? This is the thing. So here I did the derivation, but this derivation is not required. To show you, you will get confused, right? Why this type of curve suddenly coming with temperature? To show you, I just derived this one, correct? Now this is the resistivity of copper. You see how it is coming. Now this is the resistivity of the semiconductor. This is the resistivity of the semiconductor with temperature. In semiconductor, basically what will happen, the resistivity will keep decreasing if you increase the temperature. That thing we will see in the semiconductor chapter. Clear? This 3 graph is very important. You just remember these graphs or keep in your mind these graphs. Directly question come from this graph, right? So another thing I want to tell here, for this type of material, this nichrome and your manganese and constantan, so what is happening here, that the resistance is not changing or resistivity is not changing with the temperature. So resistivity almost constant. If you see the slope, there will be slightly change, but almost it is a constant, right? The resistivity, there will be no such variation of the resistivity with temperature. Here you see that huge variation, right? But here it is not huge variation, the resistivity almost constant. So that's why many devices this we are uses, right? We'll see in the in lab, some instrument will see they use this nichrome or constantan wire, right, to maintain the resistivity constant with the temperature, right? Okay. Here it is varying exponentially, but here it is slowly varying, right? Okay. Now let's do some problem. The resistance of platinum wire at 0 degree. So resistance of platinum wire they have given at 0 degree Celsius. This is 2 ohm, and 80 degrees Celsius, this is 6.8 ohm. The temperature coefficient of resistance they are asking. So you know that R equal to R naught 1 plus alpha delta T. So let's take 0 is your T naught. So you can write here R is the temperature at 80 degrees Celsius. So I can write 80 is equal to R naught is how much? 2 ohm. Sorry. This is not 80, na? This is 6.8. This will be your 6.8 ohm is equal to R naught is your 2 ohm into 1 plus alpha. Delta T is how much? 80 minus 0 degree Celsius. Right? 80 minus 0 degree Celsius. I am just putting out the 0 degree Celsius outside. Clear? So it will coming 3.4 is equal to 1 plus alpha into 80 degree Celsius. Right? So this will be your 3.4 minus 1 will be how much? 3.4 minus 1 will be 2.4 divided by 80 equal to your alpha. And alpha unit is inverse of degree Celsius, right? Because it's temperature inverse. And you can find out here, this will be obviously, this you can write alpha equal to, here I can write 24 by 8 into 10 to the power 2 here. So this will be your minus 2, right? So 3 into 10 to the power minus 2. This will be 0.03 degree Celsius inverse, right? You see here. Oh, they have given 3 into 10 to the power minus 2 degree Celsius inverse. Correct? Now go for this question. The resistance of the wire in platinum, the platinum wire, or platinum resistance they are using as a thermometer, right? Sorry, they are using thermometer. At ice point is 5 ohm. So what they are saying that at ice point means what? 0 degree Celsius. At 0 degree Celsius the resistance is 5 ohm. Clear? At steam point it is 5.25. That means 100 degree Celsius here steam point. This will be 5.25 ohm. Clear? When the thermometer is inserted in a unknown hot bath, the resistance found to be 5.5 ohm. So temperature that you don't know, you have to find out this one, and the resistance you know, that is 5.5 ohm. Clear? This thing you know. They are asking this temperature. How will do this one? So first of all you have to find out the alpha value, right? So you just see these two things here. So I can write R equal to, so what I can do here? So I can write R equal to R naught 1 plus alpha delta T. So R, I am just taking these two things. R is your at 100 degree Celsius, how much resistance? This will be 5.25 is equal to R naught is how much? 5 into 1 plus alpha delta T. Delta T will be 100 minus 0. So 100 minus 0. Right? So here you can get what? Alpha equal to 5.25 divided by 5 minus 1. So here I can say 5.25 minus 1, right, into 1 by 100. So how much it is coming? So 0.25 divided by 5 into 1 by 100. This is your alpha value. Correct? Now here you just see, just compare this one and this one, right, at 0 degree and T. So here you can say that your resistance at temperature T will be 5.5 equal to R naught is how much? We'll take 5 ohm into 1 plus alpha value you got now, right? Alpha is how much? 0.25 divided by 5 into 1 by 100 into delta T. Delta T will be T minus 0. That thing you have to find out. So how much it is coming here? So we will say that this will be 5.5 minus 5, right? Or you can multiply here. So this will be 5.5 equal to 5 plus 2.25 divided by 100 into T. So this will be 0.5 into 100 divided by 0.25 equal to your T. Clear? this is the case, right? So you will say that this will be 0.25, we will going to up, then 100. So 100 by 25. So I can write this one will be 5 into 10 divided by 25 into 100 here. So this will get cancelled out and this will give you 4. And if you will do 20, then this will be 200 degrees Celsius. So this will be your answer, right? So like that you can find out. Here you have to apply 2 times, right? Because 3 temperatures are given. So you apply like this and you can get the at 200 degrees Celsius the temperature will, the resistance will be 5.5 ohm. Clear?